Recall that limits are all about what y value we're approaching, not necessarily what y value is actually there. So first, starting with the limit as x approaches -1 from the left, remember that negative means from the left. As I approach my x value of -1 from the left, I approach a y value of -1. Now my real value at -1 is 2, but from the left I approached a y value of -1. Now my limit as x approaches -1 from the right is going to be that y value at 2, because from the right I am approaching the y value of 2. My limit overall, remember, for a limit to exist, I have to approach the same thing from the left and from the right, and that is not happening. So I would say that the limit at -1 or as x approaches -1 does not exist. A few others, my limit as x approaches 1. As I approach 1 from the left and from the right, my y value is approaching 2. So don't be tricked by the fact that f of 1 is actually 3. My limit approaches a value of 2. And then for my last one, my limit as x approaches 3, remember I do have to approach the same thing from the left and from the right. So since I don't have a right of this value, I would say this does not exist as well. When finding limits algebraically, our first step is always to plug in the x value. Sometimes if the function is simple, that's all we need to do. We get out the y value that we needed and we're done. If that does not work, if we end up with 0 over 0, then we want to finagle it. Maybe we've got to multiply by the conjugate. Maybe we need to factor something and cancel, but something should cancel if we get 0 over 0, and then we can go ahead and plug in the x value. Your other way that you could attack this, if you plug it in and it doesn't work out, if you've got 0 over 0 or plus or minus infinity over plus or minus infinity, you could use L'Hopital's rule. That is really only useful if the top and the bottom are easy to differentiate. And then our last step, once you've either finagled or you've used L'Hopital's, our end step is again trying to plug in that x value to see what y value comes out. So example 1, plugging in 2 first to see if that works out. We are going to get 0 over 0. So that tells me I should be able to simplify it in some way and cancel out a factor x minus 2. If I factor the top of this, I'm going to get x plus 3, x minus 2. Notice that this factor and the denominator are not exactly the same, but they both have, their signs are completely different. So if I do factor a negative out of one of the factors, that is going to make it a positive x and a negative 2 in both. So now I can cancel my x minus 2's. And now I'm back to my original objective of plugging in that value of 2, where I'll get 5 over negative 1. So negative 5. This is the perfect type of example to use L'Hopital's rule because I did get 0 over 0, so indeterminate form, I'm allowed to use it, and then taking the derivative of the top and the derivative of the bottom is very simple. So the top is going to be a 2x plus 1, the denominator is a negative 1, and then now I can plug in my 2 and get 5 over negative 1, just like I did the other way. On example 2, same thing. I want to plug in that value of 9, and I will end up with 0 over 0 again this time. I do want to approach this one a little bit differently since I've got that radical in there. I'm going to multiply by the conjugate, so a radical x minus 5 plus 2, and then the same thing in the denominator. So what's going to happen in the numerator is that since they're going to end up being a difference of squares, so when I FOIL, I will end up with my radical x minus 5 times radical x minus 5, which is just x minus 5. My middle terms are going to go away, my 2 radical x minus 5 and my negative 2 radical x minus 5, and then I'm just left with that negative 2 times 2, so negative 4. In the denominator, we just want to leave this where we've kind of mock multiplied, so I'm going to leave it as x minus 9 radical x minus 5 plus 2, because what will happen is that my numerator is an x minus 9 as well. We'll cancel with the x minus 9 in my denominator, and now I should be able to plug in 9 to get 1 over, let's see, that would be a radical 4, so 2 plus 2. So I should get 1/4. Okay, again, I could attack this one using L'Hopital's rule since I got that 0 over 0. So If I take the derivative of the numerator, I should get a 1/2 x minus 5 to the negative 1/2, and then over 1. So because that denominator was so simple, this is kind of nice for that, because now when I plug in 9, this will all be in the denominator, but I'll have times this 9 minus 5 is just going to be 2, or sorry, will just be 4, and then I'll end up with 1 over 4, just like I did in the first one. A lot of evaluating limits is just about problem solving, so go ahead and pause the video and see if you can go through number 3, 4, and 5 on your own. So for number 3, we needed to get a common denominator in the numerator so that we could combine that numerator. Then we're flipping that denominator and multiplying. We did have this same situation as number 1 where we have the 2 minus x, and then the other one was a negative 2 plus x. So we needed to factor out a negative 1, and then I can cancel my 2 minus x's and plug in my 2. Don't forget the negative, should get negative 1/4. For number 4, it looks kind of different here, but I noticed that when I plug in 1, I don't have any issue with plugging in 1. I would have to know that the inverse tangent of 1 is pi over 4, because the tangent of pi over 4 is 1. The inverse sine of 1 is pi over 2. Combining my denominator here, so my 1 is a 2 over 2, that means that this would be a pi plus 2 over 2. So flipping it, I would be multiplying by 2 over pi plus 2. And then I can cancel 2's across, and that leaves me with a pi over 2 pi plus 4. So that one was D. And then our last one just came from our graphing from earlier, knowing that my limit as x approaches 3, since it's not the same from the left and the right, it does not exist. For limits at infinity, we want to know that as x gets closer and closer to infinity or negative infinity, will it eventually be bounded by a y value, or will it keep going up or down forever? So in order for it to be bounded, it has to have a horizontal asymptote. So that brings in our comparing the powers, that if it's bigger on bottom, then we'll have a horizontal asymptote at y equals 0, so that will be our limit. If it's bigger on top, that means that there's not a horizontal asymptote, so our limit is going to be a positive infinity or a negative infinity. If we have an eats DC situation, we'll divide the coefficients in order to get that the limit is going to be at whatever that horizontal asymptote is. So just a few examples here. For the first example, we're approaching negative infinity. We notice here that we will have a horizontal asymptote since it's eats DC. We have a horizontal asymptote at 2/3. So that means that our limit is going to be bounded at 2/3. That's where our y values are going to get stuck. For example 2, we've got a bigger on top situation, so that means that there's no horizontal asymptote. It has to be going to positive or negative infinity. I can plug in my positive infinity or kind of plug in bigger and bigger values for x to see what could happen here. And I can note here that the numerator is going to be getting bigger and bigger, positive numbers. Same thing is going to happen with the denominator. So it is going to go to a positive infinity. But remember also, when I'm plugging in this infinity, I'm really getting infinity over infinity. So I can use L'Hopital's rule. If I take the derivative of the numerator, I'll get 2x. The derivative of my denominator is 3, which I still have to consider plugging in larger and larger values for x, but it's a little bit more obvious to see that it's going off to a positive infinity and not a negative infinity. If we look at that exact same problem, but approaching a negative infinity instead of a positive one, I have to consider that my numerator is still going to go off to positive infinity because I'm squaring those values, but my denominator will go to a negative infinity. That means that my overall limit is going to be a negative infinity. Using L'Hopital's rule in this case is a little bit easier, I think, because when we simplify it to that 2x over 3, we can see if we plug in larger and larger negative values, then this is going to end up being a negative infinity. Two specific limit values that we've looked at before both involve trig limits when x is approaching 0. So if we see x approaching 0 and then it has sine or cosine in there, it might be one of these limits. And remember that we use these that we memorized to manipulate anything that involves them. So looking at example 1, we've got that x approaching 0, and then I know that I've got sine of some theta over that theta. Now these have to be exactly the same in order to say that it equals 1. So this is where some finagling comes in, where if I need a 5 in the denominator, it's fine to add that in there, but I can't just multiply by 1/5, so I do have to multiply the whole function by 5 over 5. This whole piece of it, when I take the limit, will end up equaling 1. And then that 5 was just a coefficient, so the whole limit ends up equaling 5. For example 2, similar situation as far as having that sine of x over x, but then we also have this piece as well. Remember that with limits, we are allowed to split this into two different limits, where we've got the limit as x approaches 0 of 2x over x, plus the limit as x approaches 0, sine x over x. So for the first part of this, since those x's cancel, our limit is just 2 because I can't plug in the 0. And then my limit here from what we had above is 1. So our whole limit is 3. I want to end the limits review with 2 questions for you all to try on your own. Don't let the word challenge fool you. Both of these are very doable. So pause the video, try these on your own. You can do it. So for challenge number 1, if I try to plug in 0 at the very beginning, we see that we're going to end up with this undefined piece for 1 over x. But if I go ahead and distribute the x to everything, then this x over x is just 1. Make sure you don't make it 0 when they cancel, that it is x over x is 1, which does allow us to plug in 0 for all of the x's, and you should end up with the limit of 1. Challenge number 2 takes a little bit more analysis. First, notice that since we have sine and cosine in there, but we're talking about the limit as x approaches infinity, so I'm not thinking about those memorized sine and cosine limits that we looked at earlier because we're not approaching 0. But if I'm approaching infinity, if we know anything about our sine and cosine functions, it just means that they're going to be oscillating. Sine just keeps going back up and down, and same thing happens with cosine. They never have values that are below -1 or above 1. So sine and cosine are both going to be oscillating between -1 and 1. So that means that really the only important part of our limit is that e to the x, because our function is going to be stuck in between those values both being -1, those values both being 1, back and forth. They're going to be somewhere in between there. So if we analyze that e to the x piece, as x goes to infinity for e to the x, it is going to go to infinity. And then we also know that 1 over infinity, or 1 over e to the x, is going to go to 0. So that means that our limit is actually oscillating in between 0 and 0, or it's approaching it at least. So by the squeeze theorem, the limit actually has to be 0.